So let's say for the next function, we want to translate our parent function over here to this one, which is y is equal to negative 3 root x minus 2. So what we see immediately, again, what we did last time is we're going to identify the a, b, h, and k. And that way we know what to apply to the point. So we can see that our a is negative 3. The b is equal to 1. So I'll just write b is equal to 1. There's nothing there. And of course the h, now since this is a minus 2, when we set it to 0, it would actually be a plus 2. So we're going to write h is equal to plus 2. And there is no k, so that'll be 0. Okay, now, with regards to the a value, since it's negative 3, that means that there's a reflection over the x and a stretch by 3, and it's actually a times 3. B, there's no change, and there's no negative right beside the x, so there's no reflection either. So we'll leave it the same. And then h tells us that we're going to move 2 units right. So just like we did in the previous problem, we're going to take our x coordinates and the y coordinates of the original function, which is 0 and 0, 1 and 1, and then 4 and 2, and that's your x and that's your y. And then using the algorithms, right, and we'll write it over here where your y prime is equal to a times y, which is the old value of y, plus or minus k, and x prime is equal to x over b plus or minus h. We're going to apply it to each set of points. And so if I look at the 0 here, so for the x, and I'll just take care of all the x values first, put a little box x, we'll go x prime for the 0 is equal to 0 over b, which has a value of 1, as we said over here. And then plus h, and h is plus 2, so we're at plus 2, which means that this will have a new value of 2. So I'm going to scratch that out and put 2. And then for x prime at the 1, we're going to go 1 over 1 plus 2, and that's going to give us 3. So I'm going to scratch that out and put 3. And then for the 4, we're going to go x prime is equal to 4 over 1 plus 2, and the x prime would then be 6. So we scratch that out, and we'll put 6. Okay, so we're going to go y prime for the y value starting with 0 is going to equal to the a value, which we said was negative 3, right? So we're going to go negative 3 times 0. Let me write that a little bit better here. And then there is no k value, so we'll do plus 0. So this one is still going to be 0. So we don't need to cross that 0 out, but now let's do the 1. We're going to go y prime is equal to negative 3 times 1 and then plus 0, since there is no k. That gives us a value of negative 3. So instead of 1, we're going to write negative 3. Okay. And then the y value of 2, when it gets transformed according to the function, we're going to go negative 3 multiplied by 2 plus 0, and that's going to give us negative 6. So we scratch that out and we put negative 6. Now all we do is we plot these new points. So where x used to be 0, now it's going to be positive 2. So we're going to plot our first point over here. Secondly, where x is 2, y is 0, sorry, we already plotted the point. Now we're going to go to where x is 3, y is going to be negative 3. So we're going to go 3 over here, and then move down 3 units. 1, 2, 3. And now this is the new point, the second point. So I'm putting a little check every time I complete a point. Then we're going to go to x is equal to 6. So 1, 2, 3, 4, 5, 6. And we see that at x equals 6, y is negative 6. We'll go 1, 2, 3, 4, 5, 6. Okay. And so there was a reflection over the x-axis, so it inverts, much like our last one. And our transformed graph function of negative 3 root x minus 2 is as follows. And I'll just write that down over here in case that got a little confusing. Okay, so eventually where we want to get is to be able to do these kind of transformation calculations in our heads, so you don't always have to go through the entire long process like I'm going through here. Now we're going to go backwards. We're going to give you a graph and we're going to try and determine the transformation function. So let's say I have the blue function here, which would be the transformed function. So this is one that has been transformed. And we want to find out what the transformation function is. So we know that this one above is y is equal to root x, right? And so one thing I'll say is this. If you look at the arrows, so here's one arrow and then here's the other arrow, that often tells you where the graph starts and finishes for both the transform function and the parent function. And that's important because sometimes if we flip it over the x-axis, or the y-axis, sorry, if we flip it this way, this is flipped over the x. If we flip it over the y-axis, that arrowhead can change. And sometimes there can be a reflection over the x and the y. And so you could see that arrowhead over here face the other way while it's been transformed. So we kind of use that as a guiding point. What we can see over here is that this, first and foremost, I can see that the graph has been reflected over the x. And it's not just because it's below the x. We can see that because this graph curves down, whereas the other one curved up. And so when that happens, you know that there's a reflection over the x. So what that tells us is that a has to be negative. Now that arrow is still pointing towards the right over here. Okay, so this one is still right. So that means that there was no reflection over the y. And I'm writing that here, over y. Because if there was a reflection over the y, you would see the arrow pointed the other way. So it could be, if I redraw it over here, right, it would be something like, let's just, for argument's sake, show what it would look like. If it was reflected over the y, then we could see that the arrow points, in fact, the other way. It would be pointing this way as opposed to the other way. Okay, so if you see the arrow pointing the opposite direction, that usually means that there was a reflection over the y-axis. But in this case, it wasn't, so we can gather that there was no reflection over the y, but there was a reflection over the x. So if there's no reflection over the y, that means that the b is still positive, if there is a b value at all. Okay, now, another thing that we can see is that there has been, okay, and I'll go to the highlighter again, there has been a horizontal shift. If we look at the first point here, which started at 0, well, now the first point of the transformed graph starts at 2, which means that there has been a horizontal shift 2 units right. Now what does that mean? That means that the h has a value of positive 2. So that gives us some information to start, because we can see, right, that we can see that when plugging into our formula, which would be y is equal to a root x minus h plus k, well, now we have a value of the h that we can get started. with. So we're going to go, at the very least, y is equal to a and then x minus 2, since it was moved 2 units to the right, going this way. Okay, in every point, if we were to look at every point, we could see that every point was moved by that. So if we look at the second point, which started at 1, well, in the blue graph, that second point now started at 3, which is 2 units away. And of course, this keeps going and going. So we know now at least it's ax minus 2. Now, is there a k? Well, once again, look at the points. If I look over here at the first point here didn't start over here or down here. It actually started at the same spot as the original point vertically. It started vertically at the same spot. We know that there's a horizontal translation, but vertically there doesn't seem to be a translation. So if there's no vertical translation, and I'm going to write that here, no vertical translation, well, then the k has to be 0. So we don't have to write the k value here. So what we're going to do is, now that we know that it's y is equal to a root x minus 2 and that the a is negative, we can use any of these points over here and sub in the values for x and y to help us determine what the value of a is going to be. And once we determine that algebraically, then we can just slap a negative on there. Because we know it's negative, we can see a reflection over the x. So let's say if I were to pick this point, and I could really pick any of the points, I would say try not to deal with the ones that have zeros in them, just because it makes it a little bit interesting, to say the least. But let's say I pick this one, which is at 3 and negative 2. So the y value is negative 2. And then the x value is going to be 3. And then we plug it in, and we're going to isolate for the a that's outside the root. So we're going to go negative 2 is equal to a and then root 1. Now what I can do is, to remove the root 1, I could just divide both sides by root 1, which cancels it on this side, and negative 2 divided by root 1 is just going to be negative 2, and that's the value of a. Now, I said that we can put a negative on at the end. Well, that's in some strange cases. If there's a reflection on the y and x axis, you might get a positive value, and if you know that a is supposed to be negative, put the negative value, even if algebraically it comes out positive. Again, sometimes when there's two reflections, that can happen. But in this case, we see that's negative 2. So now our function so far is going to be y is equal to negative 2 root x minus 2. So we see that our graph is y is equal to negative 2 root x minus 2. And to figure out if there is a b, you could take a point and then plug it into this function already and solve for the b right beside the x. Or what you could do is go to the original graph and count how long it is horizontally. So in this case, the parent function is 1, 2, 3, 4, 5 or so units long. If I go from point to point, so because the arrow keeps going, let's just say it's 4, right? 1, 2, 3, 4. The same token, let's count the new function from point to point. So from this point over here to this point, and that is 1, 2, 3, 4. So it seems to be the same width horizontally. So we're going to say that there was no change in b. Okay, so then finally, and I'll write it in the corner here, it looks like our final function in blue is going to be y is equal to negative 2 root x minus 2. okay? And again, I think when it comes to B, just count the squares horizontally. And let's say by chance, let's say that the graph, for some reason, expanded from 2 all the way to, let's say, 8 or so. Well, then what you would do is, let's say it went all the way to here, we would count the squares. So the original parent function was 4 squares, and then I counted the transformed function, and I knew we drew it all the way to here, but we're going to mark it at the red line over here, was 8 squares wide. I say long, but it really should be wide. And to get your B value, you go like this, and we're going to erase this old work here. The B value would just be the transformed, so we're going to write transformed width divided by the parent width okay. So in this case that would be 8 divided by 4, which means that the B value would have a value of 2. But remember that the graph gets transferred by a factor that is 1 over B. So to get the actual B value, right, you would have to inverse this. And so B would be equal to 1 over 2. So this is we could even say that it's the 1 over B value is equal to the transformed width divided by the parent width. And that's the 1 over B value. Okay? And so then whatever value I get here, and I know I put B there, but it should be really 1 over B. If I want to get the B value, I just flip it like this. Again, this is only if we can see, after we've done everything else, that there is a horizontal stretch or compression.